Hi there, guys. All right, so at this point in physics, we have covered just general graphing rules. Hopefully you've submitted your graphing assignment. It's really important with graphs that you make sure you are following all the criteria, that your x and y axes are labeled with units, that you've got a title, that your x and y axis scales are appropriately spaced, that your data is plotted accordingly, and that you have a line of best fit. So we learned about the distance time graphs. Now we're going to move on to position time graphs, or they can be called displacement time graphs. The difference here is that if we think back to kind of the start of the unit, position and displacement are vectors, which means that direction matters. So if we're looking here, these two graphs, we have one that is a distance time graph and one is a position time graph. So this should really read displacement. Now notice how these two look the same. So position time graphs and distance time graphs, they really will look the same, but only if the motion is in one direction. So both of these graphs are showing geese flying south for the winter, right? So the distance is increasing for the distance time graph, and because the geese is just flying directly south, it just looks the same. Notice here with my units, when I have displacement, and I guess this should read displacement, it is important that you include the direction, all right? Now, whatever direction is indicated on the y-axis, that's what's going to be the positive direction. All right, now these two look the same only because the geese are flying in one direction, south. If the object's motion involves forward and reverse, so if the object changes direction, then the graphs will start to look different. So these two graphs, again, are showing the same motion. Both of these graphs are showing a person going to the grocery store and back. Let's start by looking here at the distance time graph. So the person started walking to the grocery store, they stopped, had to do their shopping, and then they started walking home. But because distance doesn't account for direction, it's just about the total, amount of space covered. Even though they were walking home, their distance, like if you're thinking a step counter, their distance number is still increasing, okay? So a distance graph always has to be moving in the kind of upward direction. It's never going to go down like we see over here on a position time graph, okay? So on our position time graph, it shows a little bit more about the motion of the direction. So notice here my y-axis is displacement in meters and the positive direction is west. So that same person going to the store, that would be in the west direction. Shopping, and when they come home, that means they're traveling kind of back in the east direction to where their displacement really is zero, right? They started and ended at the same spot. And this would be what the graph looks like. So in a position time graph, if the kind of line, it has positive slope and it's going upwards, that means the person is traveling in the positive direction as indicated by the y-axis. And if it has negative slope and it appears to be going down, then that means they're kind of they've turned backwards. All right. So that just summarizes this here, okay? Positive slope indicates forward motion, negative is backward. Now we don't really know, like technically a person could be walking backward or they could have likely turned around and walked in the opposite direction. A horizontal line, so straight across, means that they're actually not moving, right? Because their, position and distance isn't changing. If you have a straight, and again, this should read straight diagonal. Straight diagonal line, like that, indicates constant velocity, and a curve would mean that velocity is changing or acceleration. And again, think about slope. So if we think back to our slope formula, y2 minus y1 over x2 minus x1, in a distance time graph, y is distance, x is time, that equals speed. In a position time graph, y is displacement, x is time, which means my slope is velocity. And as we know, speed and velocity are very similar, only difference being that for velocity, direction is important, and so we have to include that. All right, so this is the summary, important summary, of summarizing how we would describe motion on a position time graph, right? So my y-axis is position, x-axis is time. Again, if this was an assignment, we should be including units of some sort. And let's say this would be west. All right, so just comparing some of the lines here. Anytime we have a straight diagonal line, so that's this one, the green line, that red line, and that red line, indicates constant steady speed, okay, like your cruise control. Comparing the green line to this red line, the green line is traveling faster because the speed or the slope is steeper. The horizontal line that goes directly across means the object is not moving, right? They are stationary. Let's say this was, 15 meters from the start. They're staying at 15 meters over that whole interval. The blue line, that's that curve I'm talking about. So that means that the object is accelerating in the positive direction. The difference here with this last segment, you would not see this on a distance time graph, but on a position time graph, this means they have changed directions and they're returning to the start. All right, so let's review that with this example. Okay, this graph is showing the position of a cat from its favorite napping place. We have the position of cat on the y-axis, units are meters and west, time on the x-axis. So we're going to describe the motion in each segment. And I'm just going to, so you can write it on this slide, I'm just going to kind of annotate here so that we can see what's happening. All right, so starting with A. What we see happening at A is really, if we look at the units, from 0 seconds to 1 second, the cat is traveling 2 meters. And because the line is diagonal and straight, they're traveling at a steady speed. So, cat is traveling, and they're moving in the positive direction. The slope is up, which is west. Cat is traveling west at a steady speed. And really, I could determine that, well, really, it's a steady, I guess I should write velocity. I can determine that velocity by calculating slope. And I can see here, if these were my 2 points, my y-axis difference is 2 meters, and my time is 1 second. So I can actually just mentally figure that out. That's 2 meters per second. And that would be west. Okay, that was a bit more detailed than you need. At B, straight horizontal line, the cat is not moving. Okay, at C, the cat is again moving west. West at a steady velocity. And in this case, it's actually 1 meter per second. The D, the cat has turned around because now the slope is going backwards. Moving again at a constant speed or velocity. So that's kind of how I would expect you to describe motion in a graph. You need to be able to recognize constant speed or velocity, no motion, acceleration, and the direction. All right, that's all you have it for now. You're going to be now working onto your workbook. Page 15 and 16 are required, and there's extra practice on page 17 and 18. So do make sure you're completing the required work, and if you are going on to physics next year, you should definitely be completing all the extra practices as well. All right, take care.